Hello everyone, my name is Shamali, Assistant Professor from SPCE. Today we are going to see about the recap session of Computer Vision in Unit 3. So we can start with that. In this session, we can see about the dense correspondence. While sparse correspondence gives us a quick skeletal model, sometimes we need to fill in all the details. This is where a dense correspondence comes in. The goal here is to find a match for every single pixel or at least a significant number of them to create a complete and detailed depth map. This is much more challenging and computationally intensive task. So it is typically done with stereo matching algorithms, which try to find the corresponding pixels in a second image for every pixel in the first. Thanks to the epibola geometry, we only have the search along a single line, which makes it more manageable. It is basically more manageable. So, early methods were often window based. They would compare a small patch of a pixel from one image to a patch in another using similarity metrics like SSD. These are the simple but can struggles with the repetitive textures or the lightning changes. More advanced methods are global meaning, or they find the best matches for all pixels at once by using an energy functions that enforces a consistency and smoothness. Algorithms like graph cuts and dynamic programming are great for this. Today, the most popular methods use deep learning, where neural networks learn to find correspondence and can produce incredible, accurate, and dense depth maps, even in a complex scenes. The dense correspondence is essential for any application that needs a fine grained or a complete 3D model, such as AR, VR, and industrial inspections. Next, we are going to see about the random sample consents, that is RANSANC. In the real world, data is messy. So, and lots of our matches will be wrong. So, how do we find the good match from the bad? The answer is an algorithm called a RANSANC, which stands for a random sample consents, as we discussed before. It is an iterative, non-deterministic method designed to estimate the model parameters even when there are huge numbers of outliers. The core idea is simple. We are looking for the largest possible groups of data points, the inliers, that all fit the same model. Here is how it works. First, we randomly select the smallest possible numbers of data points needed to define our model. For example, to find 9, we pick 2 points. Then we calculate the model's parameters. Next, we test every other data points to see if it fits within a certain tolerance. If it does, we call it as a in linear. We repeat this process over and over again, and the model that ends up with the largest number of the inlayers is considered the best one. The Ransang is a go-to tool for outliers rejection and is used for everything from finding the fundamental matrices in epipolar geometry to aligning the point clouds. It's a powerful and elegant solution for dealing with the noisy data. Next, we are going to see about the alignment. When we scan a large object or an entire room, we cannot do it all in one shot. We have to take multiple scans from different angles. This leaves us with a bunch of different 3D dataset, all in their own local coordinate systems. To create a single complete model, we need to bring all these data set into a single common system. This process is called alignment or iterations. It's a two-step process. First, we need to get a rough alignment to get a good initial guesses of a transformation. We can do this with a manual input or with a feature-based method like Ransang. Once the scans are roughly aligned, we move on to the fine alignment. The most famous algorithm for this is the ICP or iterative closest point, that is ICP. So ICP works by finding the closest point in the target scan for every point in the source scan. It then calculates the best transformation, that is the rotations and translation, to minimize the distance between all the matched pair. It repeats this process over and over again until the distance is below a certain threshold. The ICP is incredibly accurate, but it relies on the initial rough alignment. The alignment is a crucial step for combining the multiple scans into a seamless 3D models and is used everywhere, from the medical imaging to the 3D scanning. In the next topic, we are going to see about the from sparse to a dense reconstructions. So, how do all these pieces fit together? A complete 3D reconstructions pipeline usually follows a path from a sparse to a dense. The journey begins with a sparse reconstruction. We use techniques like structure from motion (SFM) to take the collections of photos and find a few key points in each. By matching these points, we can simultaneously figure it out where the cameras was for each photos and building a rough skeletal sparse point cloud of the scene. This gives us a basic framework for the reconstructions. Once we have that framework, we move to a dense reconstruction. Now that we know where the cameras were, we can fill in all the details. A common method for this is a multi-view stereo, that is MVS. This MVS is uses to the known camera position to find the dense correspondence across the multiple images. which allows us to create a rich, dense point cloud. The final step is to convert this dense point cloud into a detailed mesh. This pipeline is highly flexible and scalable, as it can take the collection of photos from a random camera and produces a highly realistic 3D model. It is basics of for the most of the photogrammatical softwares you see today, and it is robust because each step builds upon the accuracy of the previous one. In the next topic, we are going to see about the point cloud to mesh conversion. After we have created a dense point cloud, the next step is to turn it into a solid. The continuous surface that we can use for the things like 3D printing or rendering. So this process is called surface reconstruction or meshing. The goal is to create a seamless surface from a collection of discrete points. The main challenges is to figure it out both the topology, that is which is the positions are the neighbors, and the geometry, that is the optimal surface that fits the point. There are few ways to do this. A simple method is Delaunay triangulations, which works great in a 2D but is more complex in a 3D. A very popular and robust algorithm is Poisson surface reconstructions. It works by fitting a watertight surface to the point cloud by solving a special equations. This method is fantastic, but it requires that we first calculate the surface normals for each point. Another technique is Marching cubes, which is used to create a mesh from the volumetric representations like STF. The quality of the final mesh is entirely dependent on the quality of the point cloud. But once you have a high quality mesh, you can apply a texture to it to create a final or the realistic 3D models. This is the last and the most critical steps in creating a usable digital asset. Next one, we are going to see about the practical example of a 3D scanning. Let's put everything we have learned together with a practical example. When coming to a 3D scan an object, you directly apply all the principles we have discussed. The process usually starts with an active scanner. It could be a structured light scanner that project the patterns, or a LiDAR scanner that fires laser pulses. The scanner captures a series of a 3D point cloud from all sides of the object. Since each scan is in its own coordinate system, the next step is to align all of them into a single comprehensive point cloud using a method like ICP. Once we have our complete point cloud, we convert it into a mesh using an algorithm called the Poisson surface reconstruction. The final result is a highly quality or the watertight that the 3D models are ready to be used. As a cheaper alternative, you can also use a photogrammetric, which is used as a standard cameras to take a ton of photos and then reconstructs the 3D model using the same principles of the correspondence and triangulation. This is how many of the 3D models you use in movies or in video games are made. So, the 3D scanning is a great way to bridge the gap between the physical and the digital world and has a ton of applications from the manufacturing to creating the medical prosthetics. Next, we are going to see about the topic the applications in robotics. For a robot to navigate and interact with the real world, it need to be able to see. So this is where a 3D reconstructions becomes absolutely fundamental. It allows a robot to perceive their environment in a way that is much more robust than 2D vision. For example, with an object recognition, a robot can identify an object by its unique 3D shapes, which is far more reliable than just looking at flat images. So, this is also crucial for grasping and manipulations. A robot need to know the exact 3D pose of an object to plan its grips. So, for navigation, robots use a 3D reconstructions to build the maps of their environment. The most famous example is a SLAM. We call this as a simulations, localizations, and mapping, where a robot uses a combinations of cameras and lidar to simultaneously build a map and figures out its own position within the map. This allows it to safely navigate and avoid obstacles. In the world of human robot interaction, HCI or human computer interactions, the 3D reconstructions can be used to track human gestures, allowing the robot to respond to a person's action. It's also a key technology for individual automations and for a next generations of collaborative robot. Simply put, a 3D reconstructions gives a robot a sense of its surroundings, which is essential for almost every task in its performance. In the next topic, we are going to see about the applications in AR, VR, the augmented and virtual reality. If you have ever used a VR headset or AR filters on your phone, you have experienced the power of 3D reconstructions. In augmented reality, the goal is to overlay the virtual objects onto the real world. To do this convincingly, The device need to create a 3D map of the physical environment, so it's known where to place a virtual object and how they should interact with the real ones. For example, it needs to know where a table is to place a virtual object on it. It also need to handle the occultations, so a virtual object correctly disappears when a real object passes it in front of it. For virtual reality, a 3D reconstruction is used for something called inside out tracking, which uses a camera on the headset to track the user's position and prevent them from bumping into a box. It is also used to create the digital twins of a real space for things like training and simulations. The artists and developers uses a 3D reconstructions to create the realistic models for games and experiences. And with the rise of real time reconstruction, we are getting closer to a further where you can simply point your phone at a room and have it instantly converted into a full 3D model. It is technology that makes AR and VR feel truly immersive and realistic, the blurring the lines between the digital and the physical world. In the next topic, we are going to see about the challenges and limitations. So, while a 3D reconstruction is a powerful tool, it is not without its dangers or any challenges to that. One of the biggest is occultation, where part of an object is hidden from the camera, leaving the holes in the final models. We can solve this by taking more pictures from a different angles. Another major problem is a textureless surface. The passive methods really struggles to find the unique feature to match on a blank wall or a smooth white surface. This is where the active methods called become the essential one. Very tight conditions can also affect the accuracy of matches. So algorithms have to be very robust to these challenges or the changes. A tricky problem in a scale ambiguity is that with a single camera, it is impossible to know the true size of an object. A small object close to the camera can look identical to a large object far away. This is why we need a second camera or a known reference distance. And of course, there is always the issue of computational cost. Reconstructing a high resolution dense model can be incredibly time consuming and require a lot of processing the power. There is also the problem of noise from the sensors and difficulty of reconstructing the reflective or the transparent surfaces which scatters or refract the light in unpredictable way. And finally, in robotics and mapping, errors can accumulate over time, leading to a distorted map, a problem known as a drift. The last topic we are going to see today in this recap session is a summary and the future trends. To sum it all up, we have covered the key concept of 3D reconstructions. We learned how shape from X infers a 3D from a 2D cues, how active the range finding measures the depth directly, and how we represent the result as a point cloud or the mesh or even a volume. We saw how sparse correspondence finds matches for a few key points, while a dense correspondence matches a significant number of them. We also learned about the key tools like Transect for alignment and ICP for a fine tuning. Looking ahead, the field is evolving at an incredible pace. One of the biggest trends is real-time slams, which will allow the devices to build maps of the environment instantly. We are also seeing new technologies like NERFs, that is a neural radiance field, which uses AI to create the incredibly realistic 3D scenes. The future is also moving towards a generative AI that can create 3D models from a simple text prompt. We have also seen more widespread use of the implicit representation for more efficient modeling and the continued integrations of deep learning of to automate the entire reconstruction pipeline. As this technology becomes more accessible, it will be commonplace on our smartphones, blurring the line between the digital and a physical and completely revolutionary industries from the entertainment to engineering. Thank you.